Okay, this is our independent practice for projectile motion. This will be a really good thing to use to study for the quiz or the test. I suggest doing it for the quiz that we have coming up. So for number one, we have a baseball player. Here's how we're going to do this. We're going to go through and we're going to mark in the text everything that we get from it. This is hugely important. So a baseball player throws the ball horizontally off a cliff. When we throw something horizontally, we know two things right away. One of the things that we know is the initial velocity in the y direction is 0, because we throw the thing horizontally, which means all of our velocity is in the x direction. All of it. 28.8 meters tall, that tells me our delta y. And if it lands 38.4 meters away, that tells me the delta x. And I want the velocity of the ball. So our x stuff and our y stuff. Right away, before we begin, because this is projectile motion, an object moving through the air without anything but gravity pushing on it, that tells me that the x acceleration is 0 and that the y acceleration is 10 meters per second squared down. We know that every single time we're dealing with something that is thrown. Throws is our operative word there. Now, from here, again, that's going to be an always thing. It is always 0 in the x for the acceleration, and it is always 0 in the y for the acceleration. The initial velocity in the y, we know because we threw it horizontally, is going to be 0. The initial velocity in the x is what we're trying to find. My delta y is 28.8 meters, and my delta x is 38.4 meters. That delta y is down. Okay, so what we want is the velocity in the x. Well, that's just delta x over time because there's no acceleration. So what I need to do is get the time. I'm going to get that in the y direction. That's how these problems go. The first thing that we need to do is find the time, either in the y direction or the x direction. And then we'll use that time in the other dimension, whichever one we didn't find it in. So I have acceleration, initial velocity, delta y, and time. So the equation I want to use, I got to find the time. Delta y is equal to initial velocity times time plus 1/2 at squared. So we're just going to plug everything in. 28.8 is equal to 0 times time plus 1/2 times 10 times time squared. That 0 goes away, so I have 28.8 is equal to 5t squared. We'll divide both sides by 5. I get 5.7 is equal to t squared. Take the square root of both sides, and that tells me the time is 2.4 seconds. So we're going to take that time, plug it into the x direction, so our velocity is 38.4 meters divided by 2.4 seconds, giving me 16 meters per second. This whole worksheet is just practice over that. While doing a stunt for a movie, a car is to drive off the building and land on top of another building. So if the buildings are 80 meters apart, that's my delta x, and one car is going to be driving 40 meters per second when it leaves the first building, that's my initial velocity in the x. The initial velocity in the y is 0, because we're driving off the building horizontally. It's another horizontal problem. And we want to know how much taller. That's our delta y. So, x direction, y direction. I know that the acceleration is 0 in the x and the acceleration is 10 meters per second squared down in the y direction, and these are always true. It's important that you can identify that right away, knowing that when we have something driving off a building, being thrown out, being thrown up, being dropped, the acceleration in the x is 0, and the acceleration in the y is 10 meters per second squared down, always. My delta x is 80 meters. My velocity in the x is 40 meters per second. My velocity in the y is 0. Now, if we look at this, that's less information than we usually have in the y. We usually have the delta y, and we're looking for the velocity in the x. That's not the case this time. So what we run into is that we don't have enough information. There's not enough information to find time in the y direction. So we have to go over to the x direction. We must use the x direction to find time. So for what we have, delta x is velocity times time. 80 meters is equal to 40 meters per second times time. Divide both sides by 40. That time comes out to be 2 seconds. Now we're going to use that in the y direction. So in the y direction, my delta y is initial velocity times time plus 1/2 at squared. We'll just plug everything in that we have. 0 times 2 plus 1/2 times 10 times 2 squared. That 0 thing goes away, and my delta y comes out to 20 meters when all is said and done. Number 3, same idea. A man fires a rifle horizontally. What this tells me is that the initial velocity in the y direction is 0, and all of the initial velocity is in the x. So we're firing from a height of 1.8 meters, that's delta y. And the velocity of the bullet when it exits the barrel is 350 meters per second. That's velocity in the x direction. I want to know how far away does the bullet land. So we have x stuff, and we know the acceleration is 0 in the x direction. We know the velocity is 350 meters per second in the x direction. And we know that the delta x in the x direction will be velocity times time. Well, we don't have that time, so we're going to look in the y direction. In the y direction, the acceleration is 10 meters per second squared down, always. In the y direction, my delta y is 1.8 meters down, and my initial velocity in the y direction is 0. I want the time in the y direction. So the equation I can use to find that is delta y is equal to v0t plus 1/2 at squared, or v initial times time plus 1/2 at squared. So delta y, 1.8, is equal to 0 times time plus 1/2 times 10 times time squared. Just simplify that a little bit. So 1.8 is equal to 5t squared. We'll divide both sides by 5. I get 0.36 is equal to t squared. Square root both sides, and we find that the time is 0.6 seconds. Now, we're going to use that to find delta x. So delta x is equal to 350 meters per second times 0.6 seconds. That delta x comes out to be, when you multiply it, 210 meters. Again, the hardest part here, I think, is extracting information. So let's move on to the next one. Projectile is launched horizontally. Guess what? That means the initial velocity in the y direction is 0, and all the initial velocity is in the x. With an initial velocity of 18 meters per second, that is all x velocity, just like we said. After it has traveled 9 meters horizontally, so that's my delta x, how far has it fallen vertically? Delta y. If it's asking for delta y, I know I'm going to need the time in the x direction first. So in the x direction, as always, the acceleration is equal to 0. The initial velocity in the x direction is 18 meters per second, and my delta x is 9 meters. I know that delta x is velocity times time, so 9 is equal to 18t. Divide both sides by 18, and the time comes out to be ½ a second, because our 18's crossed out here. So now that we have the time, we can go to the y direction and look at what's going on. In the y direction, the acceleration is always 10 meters per second squared down. The initial velocity in the y direction is 0 because it's a horizontal projectile. And the delta y we don't know. But the time is 0.5 seconds from the x direction. So we got delta y is equal to v initial times time plus 1/2 at squared. We got delta y is equal to 0 times time plus 1/2 times 10 times 0.5 squared. So that delta y is 0 plus 1/2 times 10 times 0.25. All we're squaring is that delta y. And delta y comes out to be 1.25 meters. Question 5 looks at the graphs. We want to sketch horizontal position, so that's x stuff, and we want to graph vertical position and velocity with respect to time. So starting with the x, we're going to look at x position and x velocity with time, then y position and y velocity with time. So in the x direction, we are moving forward with constant speed. Constant speed on a position versus time graph is a line with positive slope that doesn't change. Constant speed on a velocity versus time graph is a horizontal line. In the y direction, we're just falling down. So we start off with 0 velocity in the y, and we're above the ground. We move closer to the ground with an acceleration that's down. That's why we are concave down here. It has to be a curve because we're accelerating. And then the y velocity, I start off with 0 velocity, and it increases in the downward direction. So what we're going to do is we're going to look at y. So if we look at the velocity in the x direction, it's constant and it doesn't change because the acceleration in the x direction is 0. That's really, really important. We have constant velocity in the x direction. So that tells me that the slope of position versus time, which is velocity, is also constant because the acceleration is 0 and the velocity doesn't change. Now, in the y direction, if we look at the velocity has a negative slope. It goes from 0 to a negative value because it's accelerating in the downward direction. The acceleration is constant and down. That's what we're going to have. All right, that's all we have for this one.